All right, last time we were covering the concept of NFAs. We went over the concept of non-determinism, tied that to this idea of NP completeness. NP in that case stands for non-deterministically polynomial, so the non-determinism is built right into the term. Then we talked about some differences, three major differences between DFAs and NFAs. Did anyone have any questions on those three big changes? Lambda transitions, the invention of teleportation. If NFAs can just kind of bring that into our lives, that'd be wonderful. Commuting sucks. Second one, multiple possible transitions out of the same state on the same character. So in this case, there are 2 zeros out of Q1, and we use non-determinism. We're going to explore both at the same time, parallelism. And with NFAs, there is no limit to the amount of parallelism that you can specify. If you want to add 20 CPU cores and parallelize, you can do that. This is a theoretical exercise. No limit to that. Third one is you don't have to specify every transition. You do not need trap states. If you're in a particular state and you see a symbol and that symbol isn't specified in the NFA, we immediately reject. So we do not have to reach the end of the input. So that's where we were. Any questions on that or any general questions on homework, expectations, anything else that I should make public before we get started? Okay, we will move on to this concept of why even care about non-determinism. I mentioned that our computers can't do this, right? We don't have an infinite number of CPU cores that we can task with a particular problem when we come up with it. We have limitations in our hardware. So why do we care to study it? So it's a much more interesting theoretical exercise than it is a practical exercise, but there are still a ton of theoretical results relating to the differences between non-determinism and determinism that if we can answer those questions, do affect the deterministic approach that we take to the algorithms that we write. So a lot of algorithms have a significantly easier non-deterministic solution than a deterministic solution. If we could determine that if we can solve a problem efficiently with non-determinism, then we could solve it efficiently with determinism, then that result vibrates through the entire world. And at that point, it's the equivalent of the apocalypse, nuclear war. At that, it's the digital equivalent of that. All of our security relies on the fact that these are distinct ideas. But we have not proven that this class of algorithms is actually distinct, or have we proven that they are the same? So we know, for instance, in DFAs and NFAs, that they represent the same class of language. The fact that you get these 3 extra things you can do to an NFA does not increase the power of what an NFA can represent. That's an intriguing result. Does that have anything to do with the fact that these classes of languages are different or the same? We don't know. It's an open problem. It has been for decades. So yeah, we will soon show that every NFA is an equivalent DFA. An example for non-determinism would be something you've seen, search and backtrack. Optimizing search and backtrack with non-determinism. How would you do it? Any thoughts? So you're trying to search a tree using breadth first search or depth first search. How could you parallelize or use non-determinism in that search to explore that space more efficiently? First of all, what is the complexity of those? How would that change if you use non-determinism? Yeah.
Every core go to every branch.
Yeah, you just create new cores whenever there is a branch. So instead of having to create a conditional where we explore one branch and then the other, we're going to use parallelism whenever we hit any branch on any tree and just say more branches, more cores, throw more processing power at the problem and just branch the problem. If we have infinite parallelism, then we have infinite compute power. We just allocate that compute power like we allocate memory whenever we need it with no restriction until the problem is solved. And with non-determinism, there's no upper bound on that. So regardless of the depth of the tree or the size of the branching factor, you can solve the problem in linear time with respect to the depth of the tree. Whenever you reach a new level, you just parallelize to whatever extent you need. New level, parallelize to the extent that you need. It's linear time. Rather than figuring out what is that branching factor, explore this branch, then that branch, then this branch, then backtrack. Recursion becomes useless. You don't need stacks or queues. You just need more compute power. Palpatine would have loved this idea. So make the choice either that's most likely to lead to the goal and explore that. But because you have that infinite parallelism, it's that same idea. You choose the right choice. You explore them all at the same time. And the one that returns success is the one that you do. Any of those ideas, same idea. You could use a modified version of non-determinism to some way intelligently search. And some algorithms actually do that in practice. So it also allows us to see how much work is actually required in the worst case, because it is one of the dimensions. We get to ignore the other dimension because infinite compute power. We just have to structure the problem in such a way that it's based on the depth rather than the breadth. So in deterministic, we use worst case analysis, and we just get to kind of take that worst case out of it because there's only one possible solution, the depth of the tree. So I've already mentioned the P equals NP problem is the biggest open problem in computer science. I don't know if that's actually true anymore, but it has been an open problem for decades. Again, you mathematically prove this or disprove it, instant millionaire. So this is just wording that again explains that idea. Are all algorithms that are solvable non-deterministically in polynomial time solvable deterministically in polynomial time? No proof for or against. The class of algorithms that we call NP-complete all have a polynomial time link between them. So if we could solve one deterministically in polynomial time, then we could solve all of them deterministically in polynomial time, which is really cool. But no such solution exists for any of those problems. The best solution we have for any of them is exponential. But it would kind of break everything if we could solve them in polynomial time. The entire security of the internet, where all of your money is stored or lack of money is stored, all of that is protected by NP-complete algorithms. So as soon as that becomes polynomial in nature, offensive cyber majors get their paws on that, and it's over. Your money is theirs. This is the rest of the internet. So we'll study things like this in a little bit more detail later on in the course, and a bit more theoretical sections. Do note that grammars have a bit of non-determinism built into them. Whenever we see that or symbol, we're just looking for a potential path through the grammar such that we can create the query string or not. So whenever you see that or, if you were non-deterministically trying to create that solution, you see that branch, you would need a different thread for each of those branches. So the way we write it and think about it is there is some natural conditional branching there that you could explore non-deterministically. Some group exercises with NFAs. Let's see if we can construct some NFAs and see how they might be easier to construct for some kinds of problems than DFAs. So here's problem number 1. Design an NFA for the language a to the n such that n is greater than or equal to 3. So this is just saying 3 or more a's in a row. Union AB a to the n. Note the n there is just superscripting the last a, not the entire ABA. So we have the prefix AB followed by 1 or more a's. That union says this language accepts either the left-hand side or the right-hand side. So you're going to have to somehow figure out how to accept both of those at the same time. This might be where condeterminism comes in. Rather than check, is it the left-hand side or the right-hand side? Is there a way to design an NFA such that you check both at the same time? Think about that, work with your neighbors, and we'll come together and talk about a solution in a bit.
Well, also, this is ABA to the. ABA was. ABA. This one terms as it means. But. So we don't prep states in events, so we don't need to do it. We're supposed to start with A, so we can just have the next state be A. Realistically, we don't even need to branch right now. And then here we can branch into two. If it's B, check the bottom and check the right hand side. It's A with that check the first. Okay. So let's switch the side. This we need 3 A's in a row. For it to work. So then 32. We just go one more. Also. Yeah, you're right. But so this is what I have it in questions. We can just start it.
I think that's the best we can do.
Well, you can't have a B because after you have two in a row, you can no longer do this one. Yeah, you can no longer do this one with a B. So if there's a B here, it just terminates. So yeah, this would be you don't have to have traps. Yeah, no, because there aren't trap states in Friday. You just if it isn't there, then it's just terminates. Yeah, I'm just trying to think about this.
Personally, actually, can you do it in 4? This might be a 5-stater.
Okay, so I know this isn't going to be as efficient as possible, but it's the move on itself because this is
I'll tell you what I do.
yeah, bring up actually, yeah. I think sorry, you choose to play this behavior.
Yeah, so whenever we see a superscript like this, it always attaches itself just to the nearest character unless there are parentheses. So if we wanted to repeat ABA, ABA, there would be parentheses around ABA to the end. So this is the single prefix AB followed by one or more A's.
I thought that purchase all three, like the whole language and.
Gotcha.
Yeah.
Yep, that makes sense.
Yeah, that's makes a lot.
Yeah, but you'd also have to have two different. So it'd be electric, so you have to have two different little rows. Okay. No, this is.
If you completed this first one,
That's still leaving.
well, people are finishing the first one.
Right.
Here's a second one for you to work on. And whenever we see the exponent, it attaches itself just to the nearest character, unless there are parentheses.
Start there, it's like,
It's the same order of operations as math. Exponentiation before concatenation, which we think of as multiplication. So repetition comes before concatenation.
just. That's what I'm. Right. Plus, it's in. You have to have trap state. Yeah. You have to have a trap state. Absolutely.
Do we need a trap state?
No,
Well,
because
not
we're using
saying
that
that,
as,
yeah.
Okay. So we can always just start with Q0. Which is. In the set. Part of the lambda. Okay. So then. Both of those still use the thing, we need to also send it. Also, I see, yeah, there would be a lot of like, yeah, sure. So. We have to go to A for each of those, so we'll start with A. Wasn't only the second is so alright, so I think so. Just one that would have to be a transition. And then if we're going to go this in the first half of the equation, we have number A. We have to go to a different state that's not accepted. Then go back. Yeah, because then you're all going to be able to. Yeah. So I think this is good for the first part. Okay. So, yeah, what's the second part? I'm sure you gotta go B. Or different states, B. Zero. Or that's where so you can just sleep on itself. Okay, so this. Just like there has to be at least 2 B's. Not really, because if the second B is 0, you have that B. But this is a, I don't think. Yeah, because this can be 0. Oh, it's just A B. Oh, it can't be 0. Yeah. That's you better go check with Dr. King.
Have ideas?
How are these? We did, I think we did mess up. An edge on the bottom.
Interesting. I like them.
I'm just waiting for the counterexample of the one rule that I forgot.
Second one.
I know that there's an edge that we missed, but
Yeah,
yeah.
I think it's correct. Aside from that edge that you say you missed.
Gotcha.
I like it.
Thanks.
Was this enough? I see.
All right, let's at least walk through the first one for the moment. Anyone want to walk me through drawing their solution? Then we can check out
This is the A's problem.
if anyone can find a counterexample for it, or an example that it accepts that it shouldn't be.
So we're starting with the first one?
Yeah.
Okay, so starting state, we can have our Q0. It's obviously not accepted because we don't take the empty string. From here, from the first problem set, we have to go to an A for either of them. So our Q1 has an A transition.
Mhm.
We're not even gonna branch yet because we don't need to. Now, if we have an A, we want to continue to another Q2 state, we're gonna check the first half. Just like that. And then we can go one more time to finish off that set, just to.
Yeah, we need to have 3 or more ends in order to accept. So this is the
Yep.
first one, this is the second one.
We
We need one more A in order to get to an accepting state.
and final state, and we can loop here as long as we're staying on A.
So this is a way to represent the left-hand side of this.
Mhm.
So the question now is, how do we build the right-hand side into this in a way that we're checking them at the same time? Yeah,
Transition out of Q1 to Q2 also work for me.
yeah, so the right-hand side starts with the same first A character, so this edge can represent the first A in both the left-hand side and the right-hand side. But we need some transition out of Q1 that's going to read the B that we expect from the right-hand side. So we'll go into a new Q4 on a B. So once we've seen that A and a B, we need to see one more A or more than one more A in order to be able to accept. How do we handle that, or how can we handle that?
Yeah, we could add a transition between Q4 and Q3 on an A.
Yeah.
But why can't we just go straight to to Q2 on a B?
Using this on a B?
Yeah, why can't we do that?
So something like that,
Yeah,
sure. We could do that. There's nothing wrong with doing that, or doing this, or even bringing this out.
so it can be a four stater.
There can be a 4-state solution. So again, this solves the problem in a bunch of different ways. We only need a subset of these states. You can just use Q0, Q1, Q2, and Q3. You can see the right-hand side is path Q0, Q1, Q4, Q3, or Q0, Q1, Q4, Q5. So as always, there are multiple possible solutions to these problems. Some might be considered to be more efficient if they use fewer states, but again, unless a problem specifies, show me the minimal DFA or NFA for a particular problem, I do not care. I just care that you have a solution that works. So it's all the way over there. Anyone with questions on this approach? So yeah, simplest solution ignores Q4, Q5 and all transitions into and out of them. Just using Q0, Q1, Q2, and Q3. If you don't have this transition, then you can utilize Q4 and going to Q3. And if you don't have this transition, then you need an additional Q5. And depending on how you visualize the problem, like, hey, there's a path for the left-hand side, and there's a path for the right-hand side. That's perfectly valid, perfectly fine. If you can see the overlap between the problems, they branch here, they merge back here. Or you can follow along the same path, reading in slightly different symbols. All of those are just different ways of seeing the same problem. Just like writing programs. There are good designs, there are bad designs, and there are lots of different good designs in there as well. The bad designs would be less readable than anything that I wrote that is still equivalent to it. Add 14 more states and a bunch of lambda transitions. Bad design. How about the second problem? Anyone want to walk me through a solution that they've come up with for the second problem? Yeah.
So from Q0 on an A, you go to Q1 as an accepting state. And then from Q1, you go to Q2, which is on an A, which is not an accepting state. And then from Q2, you go back to Q1 on an A. And then a Now that another state from Q1 is gonna be on a B. Which is also an empty state and you move on to B.
All right, so the left-hand side is found up here. Single A is accepting, one is odd. If we see two more A's, we go to Q2 and back to Q1, to Q2, to Q1, to Q2, to Q1. And for the right-hand side, we see an A and a B. That second B to the N is 0, so we should accept that. But we can loop and 1, 2, 3. There is something to consider here. I think we might have this here. What do we see?
The pathway for A, and then coming back in.
Yeah, what if we have a string like A, B? Is that in the left-hand side? Is that in the right-hand side? Is there a path through this NFA that accepts it? Yes. So it's a very similar type of mistake that I see on homework, where this was constructed with perfect logic. You constructed the left-hand side and it works. You constructed the right-hand side and it works. But because there is some overlap between these problems, you can create a path through this NFA that accepts a string that's not in the language. So unless you're thinking from that perspective, is there a counterexample that I can find? You might not catch something like this.
For a solution, could you have QO have two different A string or A?
You could, yeah, you could branch this to have two separate A's,
like-
where now we don't have this connection here. We kind of fully separate the first side with an A and a B. I guess this would be Q4. Little bit strange numbering system, but that would work. The other thing that you could do is break out this into an additional state out here. And then this loop, instead of going back here, loops out here. But regardless, you do need one more state somewhere to be able to handle that. So yeah, I chose the first example because it shows all of the different kinds of solutions that you can create that are all reasonably equally valid. And I chose the second one exactly to showcase this mistake. Because it is very easy to make and it's very similar to what I see on a lot of homework submissions. So make sure you take the time when you complete a homework problem to really think about it and verify. There are very easy mistakes to make on just about every problem. Questions on this construction? Feel confident enough to be able to make some NFAs on an assignment? You'll see when you get there. That's what my office hours are for. Please utilize them. All right, the next big thing that we are going to tackle is converting NFAs into DFAs, because I made this assertion a couple of slides ago that for every NFA that we make, there is an equivalent DFA. It's time that we actually show how that works. First, note that a DFA is a restricted NFA. We take the rules of an NFA and we place further restrictions on the NFA to create an associated DFA, or to have what is a legal DFA. So it might be intuitive to some that if you have one DFA, there are many possible equivalent NFAs. You could relax the constraints of those DFAs to say, let's just throw some lambda transitions to non-accepting states. You don't even need to think about adding or modifying any logic. You can create an infinite number of equivalent NFAs by just saying, we'll add an arbitrary number of states and an arbitrary number of lambda transitions from the existing states to those non-accepting states. What about the logical converse from discrete? What is a converse? Anyone remember? Or went over it in the first place? I don't know how discrete is taught, but I've heard horror stories.
know we covered it, I'm just trying to remember which reflection it is, because there's a bunch of different.
Inverse,
reflections.
converse, and contrapositive.
Yeah,
Around like state.
The way that I mimic it is I remember them in that order: inverse, converse, contrapositive. I use this idea to negate. So inverse is the negation, the converse is the flipping of the order of the if then, and the contrapositive is doing both because it's the longest word, it does both of them. So inverse, converse, contrapositive.
okay.
I don't know why that works for me, but it works really well. So the converse is just taking the if then and flipping the order. So if a particular DFA has many possible NFAs, the converse would say, if we have an NFA, do we have many possible DFAs? Yeah, that actually ends up being true. For a particular NFA, it will collapse itself into one possible DFA. So thinking about this, how would we go about this? How algorithmically, if you were designing this process, you were tasked with, okay, intuitively, you feel like for a given NFA, there is one and only one naturally equivalent DFA that we can algorithmically, deterministically determine. How would you go about writing that algorithm, inventing it? Any thoughts on that process? You might remember.
I know, but we have to
Thoughts?
add in all of our missing transitions.
Yeah, so there are quite a few missing transitions.
If we have branching paths, we need to collapse those. Because like if you have two different paths that both take A, which is legal in an NFA, you need to make it so there's one legal path.
Yeah, how would we, that's gonna be a really difficult problem to tackle, because like you can imagine, we're in a Q0 and there are two A transitions out of Q0 into different states. What does that mean? How do you work a DFA where there can only be one A transition to one other state? How do we get over that hurdle?
Don't we make it into like a set of states?
Yes, each state in the DFA is actually going to represent a set of states from the NFA. And so the DFA may have significantly more states than the NFA had, because each of those states is going to represent some subset of the states that were in the NFA. So if we have a branch to Q1 and Q2, both on A's, then we're gonna have a new state that we're gonna call Q12 in the DFA that represents Q1 and Q2 from that. So let's look at some of the intuition. After the DFA reads a string, how many states can it be in? Just one. After an NFA reads a string, how many states could it be in? Who knows? It's bounded by the number of states in the NFA. It could be in any subset of those states. Any one state, any possible pair of states after that branching from non-determinism, it could be in every state. Is that not the definition of a power set, as we talked about on the first day? If you could be any subset of sets of a set that we define. How many of those were there? 2 to the number of the states. So that is the upper bound on the number of states that are going to be in a DFA that is the representation of an NFA. So we're just going to start reworking this NFA with some subset of states that are every possibility of the subset of states that the NFA could have, based on the transitions within the NFA. We'll add transitions to those states based on the associated paths through the NFA, and we'll do that iteratively. Does doing that result in a DFA? By the end of that process, do we have a DFA? Is there any non-determinism between if we have a state for every possible subset of states in the NFA, could there possibly be any branching where there are 2 possible paths on an A from a particular state? They'll have to go from one subset of states to another subset of states, even if there is overlap between those two subsets. So, 2 to the number of states, we talked about why. Let's run through an example. Here is an NFA. You may question what this NFA does, or if it has any academic value whatsoever. It is designed to be interesting when we convert it into an associated DFA, and not really for any other reason. But let's take a look. I'm going to use a new color because that orange was dying. So some things to think about. The initial state that the NFA is in is important. Since the NFA is in Q0 when it starts, the set of states that it could be in the DFA when it starts is just Q0. However, imagine that there is a lambda transition somewhere in this. Like if there's a lambda transition from Q0 to Q2, what state could you be in without reading any of the characters?
Q0 or Q2.
So the initial state in the associated DFA would be Q0, Q2. That hybrid state consisting of the subset of states 0 and 2. So where you start depends on the subset of states that you could be in before you've consumed any characters from the input. So it's not just always Q0. But it will always contain Q0 as long as we have a consistent numbering scheme where the NFA, the initial state, is Q0. So we will start by building this together, by building this up. So there's a transition from Q0 reading an A. This NFA could be in either Q1 or Q2 after we read that A. Why?
Lambda transition.
This lambda transition. So if the input, remember we read this character at a time, is A followed by who knows what else. We start in Q0, we read this A. We need to branch here because we could possibly stay in Q1, we could teleport to Q2. So the transition from Q0 on an A in the DFA is from Q0 to Q1, Q2. So as we start to build this up, we're going to see that we do that. The initial state is Q0. On an A, we're going to go to this state that we're going to call Q1, Q2.
So is that state valid or invalid?
It is actually an accepting state, and we'll get to this somewhere in the slides momentarily, because at least one of these states is accepting.
Because the only reason you do a lambda transition is just to split off. So you could also say Q2 in the NFA would act like it's accepting.
Yeah, imagine that the string is just A. Does this NFA accept the string A? Yes. Does every path through this NFA accept A? No. But since there exists a path through the NFA that accepts that string, we accept the string as part of the language. So because of that in the DFA, we have to accept it because the NFA would have accepted it. So yes, whenever there is one or more accepting states in the set of states that is the state that you create, that state is fine. Or accepting. Questions on what we've done so far? Any clarifications I can make? What happens from Q0 on a B?
On an NFA, it would just terminate. So we would need a trap state in the DFA.
Yes. What should we label that trap state?
Unless there's a naming convention, we could name it whatever we want, but.
It should be the empty set. The null set. A set that contains no elements. There is no such state in the NFA that you could be in because we have already rejected. Since we know this is a trap state, we can just add edges back to itself on an A or a B. What we're going to loop now as we do this. So the first pass through this loop is that we ask for this starting state, what happens on every possible character in the input alphabet. So we asked what happens on an A, what happens on a B. As long as there is a state without edges for it, we need to continue to loop this process. Once we have a complete DFA, we can terminate. But we don't have any edges out of this state Q1, Q2, so we need to create them. How are we going to do that? Now you can imagine that we are both in Q1 and Q2 simultaneously. There's you and a clone of you, or two clones of you, one in each. Imagine that you and your clone simultaneously move on an egg. What are the set of states that you could be in? So one of you is in Q1, one of you is in Q2, you both move on an egg. The one in Q2 drops off the face of the earth, we've rejected. And the one in Q1 has to loop here and clone itself and move to Q2. Because after that A happens, we could lambda transition to Q2. So Q1 and Q2 are the states that we could be in after we were in Q1 or Q2 and consumed another A. So that tells us there is a self edge on Q1, Q2. We go from the subset Q1, Q2, and we end up in the subset Q1, Q2. You can think of this in terms of just processes from an OS course. The process that was here died. The process that was here ended here and also forked to here.
We're dropping the Q2 without adding a
Where do we go from Q2 on an A?
nowhere.
Yeah,
Just
but
how to represent that on there, because
it's a
wouldn't you want to?
subset of states. So we ask the entire question at once. So it's kind of the union of Q1, Q2 and the empty set. What is the union of Q1, Q2 and the empty set? Q1, Q2. We only transition to this empty set if the result of that is empty. Good point. Otherwise, we would have a non-deterministic branch. And we can't allow that in a DFA. Great point, though. Is this complete yet? No, we need to figure out what happens on Q1 or Q2 on a B. So what happens in Q1 or Q2 on a B?
The Q1 state will terminate on the fork and the Q2 state will continue to survive by getting Q0.
Yeah. So Q1 could not take this transition, it could lambda transition and kind of merge with the Q2 and then take this B to Q0. The one in Q2 would be forced to take the B to Q0, and there's no further lambda transition out of Q0. So on a B, we move from Q1, Q2 back to Q0. That's the only state that we could end up in.
That lambda transition has a weird little logic to this.
Yes, but it's very similar to forking processes. Stuff that you've probably seen in past classes, assuming you've taken OS. We leave the killing children talk to the OS course and the OS textbook. As fun as that is, warped as that is. Warped was like teleportation, it's all point. Any questions on the final design for a DFA for this particular NFA? So there were 3 states. The most states that this DFA could have contained is 2 to the 3rd. 8 states, we only used 3 of them. So there was no real reason to draw out all 8 possible states because there were no paths through this that ended up in the other 5 possible subsets of states. Other thoughts or questions or comments? Yeah.
That's a comfy rule though. Like if you're trying to make your DFA and all of a sudden you have 9 states, you're like, well, I'm doing it wrong.
Yeah.
That's a comfy
Yeah.
thing.
So we're thinking about what are the boundaries of this problem. All right. Any further questions? Anyone need anything else from the board before I erase it and move on? 3, 2, 1, gone. Recording exists, but now it's in the past. But the present, if you're looking back on it. Weird how that works. All right, so we did the rest of this kind of in person. So yes, we never ended up in just Q1 or Q2, so those states were not in the DFA. Interesting. They weren't necessary. But since all transitions are now defined, we end up with a result. Yeah,
Is there any rule against having less than the NFA? The DFA having less than the NFA?
possible, I think.
Especially because you can have whatever you want in it, but you can just make multiple just useless states, so.
Yeah.
Yeah.
You could define just the empty language as a 3-state NFA, Q0, lambda, lambda, and accept just on Q0. Then you would have one single accepting state in the DFA, Q0, Q1, Q2.
Yeah.
With no transitions out of it. Because it only accepts the empty language, the empty string as the only string it accepts. I'm gonna have you go kind of the other way. I'm gonna give you a practice problem where I'm going to give you, well, not quite. Here's an NFA. Let's see if we can convert this into a DFA. But I'll give you a couple of considerations of questions you can ask. What is the DFA's starting state? Basically, what are all of these states that we could be in without reading any binary digits? What are the possible sets of states out of that starting state? And then just loop that. What are the possible sets of states out of those states? And then those states, and then those states. So we only have a couple minutes, but go ahead and get started with this. If you want to write down the problem and continue it at home, you're welcome to do so. But we probably won't have time to go over this today. We'll go over it after we have a little bit more time to work on it at the start of tomorrow's class.
Starting Q0, right? When you put working problems, we have to see like.
Yep, 0, Q0 still.
Yeah, Q0 is its own data. You can just run in Q0. There's no branching past it. Yeah, you don't make wheel branching set because if we end up using Q0, can either go to Q0 Q0, but it ends up accepting state, right? Because if it's 0, it's accepting. It's not 0. Out there, so yeah. Because there's still something. But well, Q0 is still separate. Because you need to have Q0 that's separate because Q1 is not always going to be the same as Q0. It just includes that sometimes Q0 is not with Q1. Yeah, like because you can be in Q0 and not in Q1. You can be in Q1 and have a child in Q0. In Q1 it makes it have like a condition.
But like this is
Think of it like an inclusive group, but these are different states. Yeah, they have to be different states. They physically have to be. Like you can be in Q0, will not be in Q1, if you want Q1. I think you have to have them. I don't know, use it. It can be in a thing. Okay, with that, yeah, you have your own all this turn. Well, no, not really. We can keep Q0. So you have Q0. On the 0 and 1, you have to put a Q0 /Q. So no matter what the state changes, we have to. That is okay. If we have zeros,
Non-deterministic logic.
my brain is breaking slowly as I'm watching this because everything that I think I have an idea for, it's like I got it, and then I like look at the other half of the problem, and then it just is like, no.
Yeah, this problem has a few more states than the last one. You're trying to, if you find yourself with a 3-state DFA for this. Look back at your work,
Okay, okay.
something happened.
It's a new. Add 0 here.
I don't. Rationalize what you're saying, I don't know how to have shifts, try to rationalize it myself.
Fair. Think about it for a second.
All right, it's just about time to end class. Already somehow,
Can't leave us without the hands.
I know, right? Think about it, have nightmares about it, and we will come back to it tomorrow and get a real solution to this problem.
That's.
Yeah, I'm what.
Bill?
And.
Basically just run the same as me.